Welcome to EMWorks2D for SolidWorks. In this video, we will take a look at how to simulate the maximum load torque for synchronous reluctance machines using EMWorks2D. The synchronous reluctance motor is an electrical rotating machine that converts electrical power into mechanical power. The SynRM has the stator similar to the induction motors excited with three-phase sinusoidal source. However, the rotor structure is totally different, and it is designed in a way to generate a torque called the reluctance torque. The on-load analysis is an essential part of SynRM simulation, and in this regard, the main challenge is how to apply the proper combination of the current in order to achieve the maximum current per ampere. One way to overcome this problem is to use the Park transformation, which converts the ABC frame to a DQ frame, in order to simplify the calculation process. In the DQ system, the maximum torque generation happens whenever the D-axis and the Q-axis currents are equal. The first step to use the DQ system is to define the angle theta, which is considered the angle between the D-axis of the rotor and the phase A-axis of the stator. For this purpose, we will consider a case study of a 7.5 horsepower SynRM. By looking at the 2D model of this machine, we can see that it is equipped with 4 poles and 36 double-layer windings. These arrangements here is called barrier and is used to guide the flux towards certain directions. The first step is to determine the D-axis. It should be located in the middle of the laminated parts. The Q-axis is the middle of the path, providing the highest reluctance for the flux path. The path A-axis, on the other hand, the phase A-axis, is located in the middle of the A+/A coils arrangement. Now, let us consider the load simulation using 28A sinusoidal currents for the phases A, B and C. The speed is set to 1500 RPM, which means that the supply frequency is 50 Hz. The only parameters left to calculate is the phase shift of each phases. We know that 3 phases have 120 electrical degree shifts related to each other. Therefore, if we define the phase shift of phase A, then the others can be calculated easily. Let's look at how we calculate the phase of current angle value. After determination of theta angle for starting position of rotor, we set the D-axis and Q-axis current equal to the maximum current of the sine wave divided by square of 2. Then the Park transformation is applied to calculate the ABC phase current values at the first position. Next, the phase of current angle is calculated simply using this equation. This angle will be applied to the simulation, and the phase B and C angles are shifted by 120 degrees. Please note that these values should be transformed to time to use in the simulation. Since we already ran the simulations, we can check the results of the load torque versus time. Here we can see that for this defined current with the calculated phase shift, the average torque is around 32 Nm. Nevertheless, This machine suffers from high torque ripple. We can also take a look at the core loss results. Here we have an average core loss of 70 Watt in the stator part, while the rotor core part has a core loss of approximately 30 Newton meters. For comparison purpose, we did another simulation with the same settings but with different current phase angles. Here we can see that although the current magnitude and frequency are the same, the current phase angle is different. The average torque is around 20 Newton meters. The random choice of the current phase angle produces less torque compared to the previous study. Therefore, the current phase angle should be chosen in a way to generate the maximum torque. We can also check the flux density mapping of the on-load analysis using the current angle, which generates the maximum torque. Here we can see that the stator yoke is saturated in the case where it is facing the flux barrier of the rotor. Here we have achieved the end of this video. I hope that you find a great use of this material. You also can refer to our webinar on the on-load analysis of synchronous reluctance motor, SynRM, using EMWorks2D. And also you can visit our website EMWorks.com for more information.